What's up, AP Physics C Mechanics student? Welcome back to our elegant physics videos. Today's topic 5.4 rotational equilibrium part 2. So let's jump right in. Now the object is said to be in translational equilibrium if the forces are balanced. So the net force is equal to 0. And we can say that the F along x-axis, the summation of forces along x-axis equals to 0. The summation along y-axis is equal to 0. In simpler words, left equals right, up equals down. The object is said to be in rotational equilibrium if the net torque of the applied force is about a certain pivot sums to 0. And this can be written as tau net equals to 0. So let us begin by recalling 3 important geometrical ideas. First, in the Z shape, alternate interior angles are equal. Second, the vertical angles theorem, when two lines intersect in an X shape, the opposite angles are equal. 1 equals 3, 4 equals 2. And third, for a given angle in right triangle, let's assume this is denoted by theta. Then in right triangle, we know this will represent the 90 degree or pi over 2. And the remaining angle can be written as pi over 2 minus theta. Now, in case we wanted to calculate the cosine of pi over 2 minus theta, we can simply write it as sine of theta. So cosine pi over 2 minus theta is simply equals to sine of theta. Now, exercise 1. A 45 kilogram uniform ladder of length 12 meter leans against a frictionless wall. No friction between the wall and the ladder. The ladder's upper end is at height 9 meter above the pavement on which the lower end rests. The pavement is not frictionless, which means there is a friction between the pavement and the ladder. And actually the friction existed here. An 80 kilogram man climbs the ladder until the center of mass is 2/3 the length of the ladder from the lower end, which means the distance from the center of mass of the person to the lower end is 2/3 of the length, knowing that the length is 12 meters. In part A, calculate the magnitude of the force on the ladder from the wall. So actually we need to know what is the magnitude of this force, the force of contact or at the point of contact between the ladder and the wall, where the wall will apply a perpendicular force on the ladder at this point. Now, before we start solving, let me remind you that the system here is under translational and rotational equilibrium, so we can use both conditions here. But before that, we need to mention and state all the forces that are acting on the ladder. Now, the first force is the weight of the ladder, FGL. The second force is the weight exerted on the ladder by the person. Let's call it FGM. The M stands for the man, the L stands for the ladder. Now we have the normal push by the wall on the ladder, and let's call it FNW. W stands for wall. And since we have a friction between the ladder and the pavement, there is a frictional force here. The friction actually is opposite to the tendency of motion. The tendency of motion of the ladder is to the left, so the friction force is pointing to the right. Now, another important force applied by the pavement on the ladder, in addition to the friction, is the normal push acting from the pavement on the ladder, and let's call it FNL. Now let's apply the translational equilibrium. In translational equilibrium, we simply can say up equals down and left equals right. Now, how many forces are acting up and down? They must be equal. We have only 3 forces are acting vertically. So the FNL, actually, it's equal in magnitude to the FGL and FGM. Now, the second 2 forces, the FNW and FF, are acting horizontally in opposite direction, and they must be equal because the system is under translational equilibrium. Now here, pay attention, the FNW is equal to the frictional force, because we will need this later. Now let's apply the rotational equilibrium. In the rotational equilibrium, we should choose the pivot, and we're gonna take the pivot point to be the point of contact between the ladder and the pavement. So actually we're gonna choose it here. And why did we do that? Because since I'm looking for the force exerted by the wall on the ladder, then the other forces are not required, and it would be easier if we eliminate them from our calculation. And choosing the pivot here will eliminate these two torques from these two forces, and we will see later that. So we choose the pivot here. Now let's draw the tangential direction and the radial direction. So the radial direction should pass through the ladder, through the pivot, and this is here the radial direction. And remember, for the tangential direction, it should be always perpendicular to the radial direction. Now let's start by the first force. The first force is the FGL. We will calculate the torque of this force because we here are applying the rotational equilibrium. Now this is the force, the line of action of the force, and this is the tangential direction. Remember that there is 90 degrees between the tangential direction and the radial direction. And why I'm doing that? Because actually I'm looking for this angle, the angle between the force, the line of action of the force, and the tangential direction. Now let's apply, or let's find out the torque of this force, the torque of FGL, which is equal, first, this force is rotating the ladder in this direction. This is the clockwise direction, which means the sign should be minus sign. Now the magnitude of the force is FGL. The distance, D, represent the distance between the point of application of this force and the pivot. We know that this force, the force of gravity acting on the ladder, actually is acting on the center of mass of the ladder. The center of mass of the ladder located in the middle of the ladder. Since the ladder is a 12, then the distance will be, let's call it D2, it's equal to 6 meters. So D2 multiplied by the cosine of the angle between the tangential direction and the line of action of the force. This is similar to the ramp problem, and we always know that the inclination will be equal to the angle between the perpendicular line and the gravity. So it's gonna be cosine theta. And this will be the first force, or the first torque. Now the second torque is this one. We're gonna apply the same thing. We will draw the line of action, the tangential direction, and also here we will find that the angle is theta. Now this force also is rotating the ladder in this direction. This is the clockwise, and it means that the assigned sign should be minus. So we can get that the minus FGM multiplied by the DM, and the DM represent the distance between the man and the pivot. This distance is given by 2/3 of the length. Let's call it DM. Now the third force is the force exerted, or the third torque is the torque by the force of FNW. Now let's draw the line of action of the force and the tangential direction. The tangential direction should always make 90 degrees with the radial direction. And since this angle is theta, how did we know it's theta? From the big shape, we can draw the Z shape here. So this interior angles are equal, and this is theta. Now, since the angle between the tangential direction and the radial direction is 90 degrees, or pi/2, so this remaining angle actually is pi/2, the total, minus the theta. And we can write here that this angle is just pi/2 minus theta. And actually we are interested in this angle because this is the angle between the tangential direction and the line of action of the force. Now, what about the direction of rotation caused by this force? This force would rotate the ladder in this direction. This is the clockwise direction, and we will use the plus sign in the torque expression. So we can get that the tau equals plus FNW times dW. dW stands for the distance between the point of application of the force and the pivot point. And actually this distance represents the length of the ladder, which means it's gonna be 12 meters. Let's call it dW. Now multiplied by the cosine of theta. And let me remind you that we should here use the cosine of the angle. But since the angle is pi/2 minus theta, and we know that this can be turned into sine theta, I have used the sine theta in my expression instead of cosine pi/2 minus theta. Now, what about the other torques due to the frictional force and the FNL. Now, since the line of action of these two forces is passing through the pivot point, then the torque of the NL is equals to 0, and the torque of the friction equals to 0. Now let's apply the rotational equilibrium condition, which means we need to find the summation of all individual torques. Now we substitute the expression, which means I will use these in my condition, equilibrium condition. Now remember that we are interested in finding FNW, so we move every single term to the other hand side except of this term. And the minus becomes a plus due to this movement, I mean. Now FNW dW sine theta represent the torque due to the FNW. FGL d1 cosine theta is due to the gravity of the ladder, and the last torque is due to the weight of the man. Now let's substitute. Before I start substituting, the angle here is not given. But since we have one right side and the hypotenuse of the big triangle, let me draw this triangle where the right side, one of the right side is 9 meters, the other right side is missing, let's call it x, and the length of the hypotenuse, it is equal to the ladder length, so it's a 12 meter. Since the given angle theta here, which is exactly equals to this theta, and this theta, so it's essential to find the cosine and sine of this angle because they are explicit in my equation. Let's start with the sine. The sine equals opposite over the hypotenuse. The opposite of this angle is 9. The hypotenuse is 12. So we can write 9 over 12 and the cosine can be written as 0.75. Now to find the cosine, two important ingredients of the cosine should be given: the adjacent to this angle and the hypotenuse. Now the adjacent is not given. We need to calculate it from scratch. According to the Pythagorean sum, in right triangle, the summation of the squaring of the two sides is equal to the square of the hypotenuse. In other words, I can write 12 squared equals to 9 squared plus x squared. Now by moving this to the other hand side, 12 squared minus 9 squared equals x squared. Let's take the square root and we will get that the missing side, the adjacent, is the square root of 12 squared minus 9 squared, which is equal 7.93. Now we have the missing ingredient and we have the hypotenuse. We can now use them to calculate the cosine, and the cosine equals 7.93. This is the adjacent to the angle over 12 equals 0.66. Now let's complete here. To calculate the FNW, I need to complete the isolation, which means I should divide over dW sine theta both sides, and we'll get this equation. Now we substitute with the given values, knowing that this and this represent the weight of the ladder and the man. Now the weight in general is given by the force of gravity mass times gravity. Now if I want to find the force of gravity due to the ladder or on the ladder, we just multiply the mass of the ladder 45 times the gravity, assuming that the gravity is equal to 10. So this is going to be 450 Newton. For the man, the mass of the man is 80 multiplied by 10, so it's 800 Newton. So the gravity times the distance between the center of mass and the pivot times the cosine of the angle. Now the weight of the man times the distance between the man and the pivot, and this distance can be easily calculated by 2 over 3 times L. L represents the length of the ladder. 2 over 3 multiplied by 12 equals 8 meter. And we use 8 meter here multiplied by the cosine of the angle, and the cosine of the angle is 0.66 over the distance W, which is associated with the total length of the ladder, and it's equal to 12, multiplied by the sine of the angle, and we found that the sine of the angle is 0.75. Now we plug this in the calculator and the answer is 667 Newton. This is the force or the normal push or the force exerted from the ladder or from the wall on the ladder. Now in part 2, They want us to calculate the magnitude of the force on the ladder from the ground. So the force exerted on the ladder from the ground. Now, actually, the force, we have two forces acting from the ground on the ladder. The first force is the FNL, which is the normal push, and the second force generated also by the floor or the ground, which is the frictional force. So after we find the magnitude of each one of these forces, we need to add them using the Pythagorean sum to find the magnitude of the force or forces on the ladder from the ground. So FF squared plus FNL squared. Due to the fact that they are perpendicular, and to add two perpendicular vectors, we use the Pythagorean sum. Now let's recall the translational equilibrium to find the FNL. The FNL is equal the weight of the ladder plus the weight of the man, and these two weights are already calculated. Now 450 is the weight of the ladder, 800 is the weight of the man, and this force actually equals to 1250 Newton. Now what about the frictional force? To find the frictional force, we should use another equilibrium condition, which is left equals right. We have already calculated the FNW, and we found it to be 667 Newton. Also, if F is equal 667 Newton, then the magnitude of the force exerted by the floor on the ladder is given by square root of 667 squared plus 1250 squared, and this value is 1417 Newton. Now exercise 1. A uniform ladder of weight W leans without slipping against a wall, making an angle theta with the floor as shown above. There is a friction between the ladder and the floor, so there is a friction here. But the friction between the ladder and the wall is negligible, no friction here. The magnitude of friction force exerted on the ladder by the floor, so here we are looking for the correct magnitude or the correct expression that represent the magnitude of the friction. And as we can see here, all of these expressions are written in terms of W, and most of them also are written in terms of theta. Now, let me recall that this system is under equilibrium, which means it has translational equilibrium and rotational equilibrium. So for the translational equilibrium, one can say that the force of gravity, or let me state the forces acting on the object first. The first force is the force of gravity of the ladder. The second force is the normal push by the floor, and the friction force, and the normal push at the point of contact between the wall and the ladder. Now let's apply the translational equilibrium. Left equals right, so we can say that FNW equals to FF. Up equals down, so the force of gravity equals to the FNF. Now remember that the force of gravity has another notation can be used, which is W, and we call it the weight. So I can replace the Fg by W, because I should follow the consistency between my solution and the given notation. Now this is regarding the translational equilibrium. Remember that the translational equilibrium will give the birth for two linear equations, one of them along the vertical, the other one is along the horizontal. Okay, so now we apply the rotational equilibrium, but before we apply the rotational equilibrium, we need to decide the pivot point. Now we're gonna consider the pivot point to be at Fn, the point of application of Fnw, so we can eliminate the torque due to this force. So this is the pivot. Then we draw the radial direction, which is passing through the pivot point through the ladder, and the tangential direction. Now let's start by calculating or writing the expression of the torque of the first force. The first force will be the force of gravity. Now the tangential direction will be perpendicular to the radial direction at the point of application of this force. Now we know this angle, it will be equal to the inclination angle. So this angle is equal to theta. Now this force, actually, it's rotating the ladder in this direction. And why in this direction? Because if you consider that this ladder is rotating around this pivot, then the ladder will able to make a circular motion around this pivot, and the path, the trajectory will be in this way. So this force is actually pulling downward, which means it will rotate in this direction to complete the path or the trajectory due to the circular motion. And the force of gravity will rotate in the clockwise direction. What about the FNF? It will rotate in this direction. And for the FF, also it will rotate in this direction. So the tau of the force of gravity equals, since the tau or the gravity is rotating in this direction, this is the clockwise direction, we will use the minus sign. Now remember that we have to choose the W to represent this force. So I will follow the same notation. The distance represents the distance between the point of action of this force and the pivot. If we consider that the total length of the ladder is L, and due to the fact that the point of application of this force is located at the middle of the ladder, then this distance will be L over 2 times the cosine of the angle between the tangential direction and the line of action of this force, and this angle is theta. Now let's consider this force. This force is rotating the ladder in this direction, the FNF. Now this direction is the counterclockwise direction. So we use the plus sign for the counterclockwise direction. Now, since the FNF is equal to W, I will use W as a magnitude of FNF. Now, this point is acting here, which means the distance between the point of application of this force and the pivot point is L. Now, what about the angle? Now, the angle here should be considered to be the angle between the tangential direction. This is the tangential direction, which makes 90 degree or pi over 2 with the radial direction, and the line of action of the force. So the angle is actually this angle. This is between the tangential direction and the line of the action of the force. Now, we can say that this is the S shape, because these two lines are perpendicular, and the same line is crossing the two lines, which makes this angle equals to this angle. So this and this are equal. Now, this is theta. This is the tangential direction and radial direction, the angle between the tangential and the radial 90. And which means this angle, it should be written as pi over 2, the total, minus this given angle theta. So this is pi over 2 minus theta, which means this is also pi over 2 over minus theta. Due to the symmetry, one can say that this angle is theta, because also this is the tangential direction with the radial direction, so this is the total should be add up to pi over 2, which means this angle is theta. So this is another tangential direction here, where the angle here is theta. Now the tau of the friction equals, first, the direction of rotation here due to this force is a clockwise direction, so we assign the minus sign. The magnitude of the friction is missing. The distance is between the point of application of this force and the pivot, and this distance is L. And regarding the angle, now we need to find this angle. We know that the tangential direction and the radial direction makes 90 degree. We know this is theta, so this missing angle, it should be pi over 2 minus theta. And let me explain it more clearly. If this is 90 degree and you cross this 90 degree with a line, and if this is given by theta, then the remaining angle, which means from here to there, from the line to the right side, it's actually equal to pi over 2 minus theta. Because pi over 2 minus theta plus theta, it will give me pi over 2 again. So cosine, we are talking about this angle. This is pi over 2 minus theta. Knowing that pi over 2 minus theta, cosine pi over 2 minus theta can be written as sine. So let me change the expression into sine theta. Now we still have one remaining force. Now the torque due to this force is 0 because the line of action of this force is passing through the pivot. So the tau of NW equals to 0. Now let's add them up. Let's find the summation of these torques, and we know it's equals to 0. It's going to be equals to 0. So minus W L over 2 cosine of theta minus f of f L sine of theta plus W L cosine theta equals to 0. So we divide both sides over L. L with L cancelled out. L with L cancelled out. 0 over L, it's 0. So minus W over 2, because we have here over 2. Cosine theta minus f of f sine theta plus W cosine theta equals to 0. Let's move this to the other hand side. It becomes a plus. And so let's take W and cosine as a common factor from these two terms. So W cosine theta minus half from this term, and from this term the remaining is a plus 1 equals, because I have pulled only W and cosine theta from this term and from that term, as if I'm dividing over W over cosine theta. So if I divide W over cosine theta for the first term, it will be minus half. The minus remains, half remains. Same thing for here. If you divide over W cosine theta over W cosine theta is 1. This is the common factor here, equals to f of f sine of theta. Now this is half. So W cosine theta multiplied by half equals f of f sine theta. We divide both sides over sine of theta. Now this cancelled with this. Cosine over sine is cotangent. W times half is W over 2. And finally we'll get that W over 2 cosine over sine is cotangent theta equals f of f. And the correct answer is W over 2 cotangent theta. Okay, exercise 2. A horizontal uniform plank is supported by ropes 1 and 2 at points P and Q respectively. So initially, the plank has been supported via the 2 ropes at points P and Q. So I is acting, or the first rope is acting at point P, and the second rope is acting at point Q. The 2 ropes have negligible mass. The tension in rope I is 150 Newton. So we can conclude that due to the symmetry, the first tension, and since we having here ropes with negligible masses and the system is under equilibrium, then the tension here, let's call it F1, equals 150 Newton. Also this one here, it will be equal to 150 Newton. So one can conclude in this case that the weight which is acting downward, the weight of the rod or the plank, is equal 150 plus 150 due to the translational equilibrium, which means the weight will be 300 Newton. Now, as long as we are dealing with the same plank, the weight will be fixed, will be the same, will be constant. Now, the point at which rope 2 is attached to the plank is now moved to point R, halfway between Q and C. So we have shifted this rope to this point. Now this point is exactly at the midway between C and Q. So if we consider this is L, then the distance from here to there is L over 2, and the distance from C to Q is L over 2. So the distance from R to Q is half of this distance, so it will make it L over 4 here, L over 4 here. So we have shifted the rope to this point, and the distance from R to C is L over 4, and from R to Q is also L over 4, but the distance from C to P remain the same, which is L over 2, if we consider this is L. The center of the plank is C. Now the plank remains horizontal. After this change, the system is under equilibrium. Which of the following are most nearly the new tensions in the 2 ropes? So here we didn't change the plank, so the weight remained the same, and the weight in the first trial is 3 Newton, so the weight is the same in the second trial after we made the change. Now, after we made the change, we still have access to the translational equilibrium, so the first tension plus the second tension is equal to 300 Newton, but this time we cannot say that tension 1 is equal to tension 2 due to the fact that there is no symmetry here anymore because we have shifted the rope to a new point of application, and we have this external part on the right hand side of the rope. So there is no any symmetry between the two ropes, which means we need to use another condition. In this case, the second condition is the equilibrium, rotational equilibrium. Now in the rotational equilibrium, the tau net is equals to 0. So first we need to determine all the forces acting on the plank, and these forces are the tension force from both ropes and the weight of the plank. Now, since we are interested in finding the tension forces, we have already access to the W is equal 300. So I will choose my pivot point to be exactly at the point of application of the weight, which means at C. So this is the pivot. Now we start applying the tau for the first tension. So let's call it tau 1. Now this force is rotating the plank, or it rotates the plank in this direction. This is the clockwise direction, so we use the minus sign for this force. Tension 1 is the magnitude. The distance represents the distance between the point of application of the tension and the pivot, which means this distance is L over 2 multiplied by the cosine of the angle. Now, since this angle is parallel to the tangential direction, this is the tangential direction, and this is the radial direction through the plank and the pivot point. So whenever we found our force, or our line of action of the force is perpendicular to the radial direction, so we can immediately eliminate the cosine, because the angle in this case is 0 and the cosine of 0 equals to 1. So no need to mention the cosine here. Now tau 2, the rotational effect will be in this direction. This is the counterclockwise direction, so plus T2. And the distance now is not L over 2 because we have shifted the line or the rope to a new position. And the distance now between the point of application of this force and the center or the pivot is L over 4. Again, this force, or the line of action of this force, is perpendicular to the radial direction, so no need to involve the cosine. Let's apply the tau net. Minus T1 L over 2 plus T2 L over 4 equals to 0. Move T1 to the other hand side, so T2 L over 4 equals to T1 L over 2. We cancel L with L. We will multiply both sides by 4, so T over 2 equals T1 4 over 2, and T2 is twice larger than T1. So here we will have two important conditions. The first condition, the summation of T1 and T2 should be equal exactly to 300, which means we will suspend E because the summation is not 300. The 350 is exceeded our condition, as well as C is less than our condition, 112.5, 11, 2.5, so also it's not equal to 300. Now T2 is larger than T1. It's twice the magnitude, which means we're gonna eliminate A, because if we multiply it 75 times 2, it won't give us the magnitude of the tension, because remember, double the T1 should give you T2. Now if we multiply by 2 here, it will give me the tension. Yes, so it's equal to 200, so most probably B is the correct one. Now let's see this part, or this choice. If we multiply it by 2, it won't give me double the tension, so which means D is incorrect. The only possible choice will be B. For B, the addition of the two forces is equal to 300 according to the first condition, and T2 is twice larger T1 according to the second condition. Now, exercise 3. A horizontal rod is supported at each end by ropes I, which are attached to the rod at point P and Q respectively. As shown in the figure, the two ropes have negligible mass, and the rod has a non-uniform mass distribution such that rod's center of mass is at point R. Due to the non-uniform mass distribution, the center of mass is not C anymore, it will be R. Point C is the center of the rod. It's exactly located at the middle of the rod. The rod remains horizontal. Which of the following vectors could represent the tension T1, T2 in ropes I and I respectively, and the weight? Now remember from the previous exercise, we found that T1 plus T2 is equal to W, which means W should be greater than T1 and T2. Vectorially, this can be represented in this way. So let's assume that the direction of T1 and T2 is upward. The summation of T1 and T2 should be exactly equal to W. T1 is not necessarily equal to T2 due to the non-uniform distribution of the masses, but for sure W always equal to the summation of the two vectors. Now, since the W here is the gravity, I will need to just change the direction of my arrow. It should be downward because the gravity always acting downward. So if we add this arrow to this arrow, definitely it's not gonna be equal to the W here. Now, as well as the length of this and this cannot be equal to W, so not even this. And also this one cannot be the correct answer because it's not equal to W. Now, both of them are correct in the length because the summation of T1 and T2 is equal to the length of W as well as here. But which one is larger, T1 or T2? Let's find out. Now, also from the previous exercise, we found that if we choose the point of pivot to be at the point of application of the gravity, in this case, the point of application of the gravity will be here. This is the point of application of the gravity. So I will choose the pivot point here because the gravity always acting at the center of mass of the rod. Now let's calculate the torque for each of one of these forces. Let's start with tau 1. For tau 1, the rotational effect will be in this direction. This is the clockwise direction, so the sign will be minus times the tension, T1 times the distance between the point of application of this force and the center of mass, and the distance is D1. Now for tau 2 equals the rotational effect of this force is in the counterclockwise direction, so the sign should be plus, and the distance is between the point of application of this force and the pivot point, so D2. No need to involve the cosine because the line of action of this force is perpendicular to the tangential direction. Now, according to the rotational equilibrium, tau net equals to 0. So tau 1 plus tau 2 equals to 0. Minus T1 D1 plus T2 D2 equals to 0, which means T2 D2 equals to T1 D1. Now, so the product of T2 D2 equals to the product of T1 D1. However, D1, which is represent the distance from the point of application of the force to the pivot point, it's larger than or bigger than the distance from the point of application of the second force to the pivot point. So D1 is bigger than D2. So if this one is larger than this one, to make them equal, T1 should be smaller than T2, which means T2 is bigger because the distance is smaller. And which arrow represent this fact? In a choice B, we have T2 greater than T1, and the summation of these two vectors is W, so which means B is the correct answer. So it's not C, D, or E. Let's learn this shortcut. Whenever we have two forces are acting in the same direction on a rod around a pivot point, and this pivot or this rod is under equilibrium, which means we have translational and rotational equilibrium. So for the rotational equilibrium, the condition can be written as tau 1 equals tau 2. where tau1 is the torque of the first force or due to the first force, and tau2 is the torque due to the second force. So no need to evaluate the sign, the angle, the distance here, because the two torques are equal, and they can be written as, if this is d1 and this is d2, tau1 can be written as f1 d1, and tau2 is equal f2 d2. Let's get started now with exercise 5. A rod of negligible mass I pivoted at a point that is off center, so the length L1 is different from the length L2. The figures above show two cases in which masses are suspended from the ends of the rod. In each case, the unknown mass M is balanced by a known mass M1 or M2. So in both cases, we have rotational and translational equilibrium, but specifically here, we are caring more about the rotational equilibrium. And the tau net in the first case equals to 0, as well as in the second case. The constant in the two trials is the small mass M. So only M1 and M2 change, or has it changed? What is the value of M in terms of the unknown masses? Now, since here we have a rotational equilibrium, so we can say that the force of a gravity, or the weight of now for the first trial, we can write that tau1 equals tau2 here immediately. Tau1 is the torque due to the first force, so the first force is mass times gravity, and tau2 is mass capital M1 times gravity. Now we just can write that force times distance 1, the distance 1 is L1, distance 2 is L2. So mg L1 equals m1g L2. Now g with g cancelled out, and we can write that mL1 equals m1 L2. Also here we can come up with another equation. The system is under rotational equilibrium, so again tau1 equals tau2. The two forces acting here are m times g, and for this one is m2 times g. Now we have a new mass here. Now m2g, the torque is given by m2g multiplied by the distance between the point of application of this force and the pivot, which written as L1. And for tau2 is mg multiplied by L2. Now g with g cancelled out, and the second equation is m2 L1 equals mL2. Now we divide 1 over 2. So mL1 over m2L1 equals m1L2 over mL2. Now cross multiply, and we'll get that mL1 times mL2 is m squared L1 L2. And here m1 m2 L1 L2. Now L1 L2 cancelled out. So m squared is equal m1 m2, and m equals square root of m1 m2, which means the correct answer is Z. Exercise 6. A uniform beam of weight W is attached to a wall by a pivot at one end and is held horizontally by a cable attached to the other end of the beam and to the wall, as shown above. T is the tension in the cable, which makes an angle theta with the beam. Which of the following is equal to the tension T? Now we know this beam is under translational and rotational equilibrium. However, here we are interested in applying the rotational equilibrium. So let's start by stating all the forces acting on the beam. The first force is the tension force due to the cable. The second force is the weight of the beam, which is acting on the center of mass of the beam. And the third force is the reaction from the pivot. We don't know what is the direction of this reaction. It's not perpendicular. This is not normal push. So we can draw it in random way. But since the pivot point is here, so the torque due to this force will be cancelled, because the line of action of this force is passing through the pivot. So let's draw the radial reaction passes through the pivot, and let's add the tangential direction on the point of application of this force, of each one of these force. Now the torque of the weight equals to, now the rotational effect of the weight is in the clockwise direction, so we use the minus sign, multiplied by the weight, multiplied by the distance between the point of application of this force and the pivot point. And let's assume that the total length of the beam is L. Then this becomes L over 2. Since the weight, the line of action of the weight is perpendicular to the radial direction, then no need to involve the cosine. Now for the tau of the tension is equal to, the rotational effect of the tension is in this way. So this is the counterclockwise direction, so you use the plus sign, multiplied by the tension, multiplied by the distance between the point of application of the tension and the pivot. This is the distance between the 2 points, which means it's equal to L. Now what about the angle? Now we consider not this angle, because the angle of the formula is the angle between the line of action of the force and the tangential direction, which means we are talking about this angle, and we know that this angle is equals to pi over 2 minus theta, due to the fact that this is pi over 2. If we remove theta from the pi over 2, we will able to get this missing angle. So this angle is pi over 2 minus theta. We know that the cosine pi over 2 minus theta can be written as sine of theta. Now we just write minus WL over 2 plus TL sine of theta equals 0. We move the WL over 2 to the other hand side. TL sine theta equals WL over 2. L with L cancelled out. Remember that we are interested in finding the tension. We move sine theta to the other hand side. So T equals W over 2 sine theta, and the correct answer is B. Now exercise 7, a 12 kilogram plank which is 4 meters long is attached to a wall by a hinge on its lower end. A rope attached to the plank at a distance of 1 meter from its free end. Now the angle that the plank made with the wall is 37 degrees. What will be the tension on the rope? Now we are interested here in applying the rotational equilibrium condition. So first we need to decide the pivot point. I will choose the pivot point to be here. Now we add all the forces acting on the plank. We have exactly at the middle the weight of the plank, the tension acting here, which is 90 degrees with respect to the plank, and the reaction of the pivot. So let's apply the tau net equals to 0. The first tau due to the weight. Now tau equals the rotational effect of this force will be clockwise direction, so we use the minus sign. The weight of the plank, let me change the letter to P. Now the distance 2 meters, let's call it D1. Now the angle here from the Z shape, we can say that this angle, this line is parallel to this line crossing with the same line, so the interior angle are equal, so this one is 37 degrees. So cosine 37 degrees. This is the tau of P. Now tau of the tension equals the rotational effect will be in this way. This is the counterclockwise, so plus T times the distance, and the distance from the point of application to the pivot, it will be 4 minus 1, 3 meters, and let's call it D2. Times the cosine angle between the tangential direction and the line of action of the force. And since this force is perpendicular to the radial direction, it makes 90 degrees with the radial direction, then no need to involve the cosine of the angle here. Okay, so now we can write down it equals 0. So minus WP D1 cosine 37 degrees plus P D2 equals 0. So T D2 equals WP D1 cosine 37 degrees. We divide both sides over D2. D is equal WP D1 cosine 37 degree over D2. We substitute now. The weight of the plank is 120 Newton, mass times the gravity. The distance D1 is given by 2 cosine 37 degree over the distance 2, which is a 3. So the tension is equal 48, approximately 48 Newton. So the correct answer is A. And that's it for today's lesson on 5.4 rotational equilibrium part 2. Thank you for joining me. See you next time.